Well, good afternoon, everyone. I hope you can all hear me okay. Welcome to the safety session of the 11th SESAR Innovation Days. My name is Luis Barbero, and I'm going to be the chair for this session. I am wearing actually a number of hats today, so I will briefly introduce myself before going into the details about the session and some housekeeping rules. I am one of the directors of GATCO. GATCO is the Guild of Air Traffic Control Officers, a professional organization in the UK which represents civil and military air traffic controllers and ATM staff. I'm also employed by NATS. I'm the Terminal Control Safety Improvement Manager. And last but by no means least, I'm also a Heathrow Approach Air Traffic Controller. In terms of the speakers we have here today for this session, we have Irene Buselli from Zenabite, we have Christian Verdonk from Crida, and Boris Resnick from GLONASS Union. And I'm sure you've attended previous sessions of this event, but just as a quick reminder, you are encouraged to ask any questions you may have in the Hoover Q&A window, and that it would help the running of the session if you could ask those questions as they come to you rather than wait until the end of the presentation. You also have the possibility to vote for any of the questions if you think that any of them are particularly relevant, so I can prioritize them in case we don't have time to get through all the questions. But in any case, do not worry, because the questions will remain in the Q&A window, so presenters will still be able to address any unanswered questions during the session. And without further ado, we're going to go into the first presentation today, which is natural language processing and data-driven methods for aviation safety and resilience, from extant knowledge to potential precursors. It is going to be presented by Irene Buselli. Irene is a data scientist at Zenabite, a spin-off from the University of Genoa, and Irene holds an MSc in mathematics, stochastics, and data science from the University of Turin, and her main area of expertise is the application of data analytics to the transportation domain. I shall hand over to Irene for the presentation, and Irene, the virtual floor is yours. Thank you.
Hi, everybody. Thank you, Luis. Can you see my screen?
Perfect.
Yes.
Okay, thank you. So as Luis was saying, I'm going to present this work, which is called Natural Language Processing and Data-Driven Methods for Aviation Safety and Resilience, from extant knowledge to potential precursors. This work was carried out together with a wonderful team whose names you can see here in the right side of the slide. And it was carried out in particular in the framework of the project FARO, which with some creative effort is the acronym of Safety and Resilience Guidelines for Aviation. This project is a SESAR exploratory research project, and was led together with all the organizations you can see here in the slide. The project mainly addresses the evaluation of the impact of automation solutions on resilience, performance, and safety. In particular, in this work, we focused on a manifestation of ATM safety, which is the loss of separation. Our approach was threefold. The first step was an exploratory data analysis on safety reports, combining state-of-the-art techniques like topic modeling, in particular latent Dirichlet allocation, and hierarchical clustering. The second step was the development of an algorithm able to extract taxonomy factors from the free text of the reports based on syntactic analysis. And the third step was the development of a machine learning model able to automatically assess contribution and to say if the ATCO contributed to the incident, if the pilots did or both did, a few minutes after the loss of separation based on operational data. So the idea is that the first two steps are something that analyzes the reports, so it's posterior to any investigation, while the third step is something that it is by now trained on the reports, but in the future it's planned to be a tool to be used immediately after the loss of separation, so before the investigation even begins. The main sources of data for this work are two. The first one is the collection of SANITA loss of separation reports. They are written in Spanish and are published by the Spanish Safety Aviation Agency, and they cover safety-related occurrences happened in the Spanish airspace between January 2018 and July 2019. There are only 89 reports. These incidents are just a subset of the total amount of losses of separation in that period, but this is the one. They are the ones that are reported due to their high severity and high importance. The second source are contextual information in structured form. They are provided by NIDA and CRIDA, and in particular, they are high granularity ATM data, such as flight tracks and ATM processed information about Spanish airspace. More precisely, there were two data frames. The first dataset are flight tracks and related contextual flight information, for instance, the flight type, the speed, the heading. And the second data frame was ATC events of interactions between ATCOs and controller working positions. So, for instance, authorizations, messages, and so on. So the first phase was a topic modeling phase, and topic modeling is a natural language processing technique able to extract recurrent topics from a collection of documents in a completely unsupervised way. Here you can see two little examples. The one in the center are some extracts from some reports where a high load of work is reported, and indeed our model completely automatically outline that there's a group of words which is workload, alone, high workload, which is always connected and identifies it as a topic. And the same is for the second group of reports where helicopters extinguishing fire are detected to be a topic. In particular, we identified 12 topics. Each topic is defined from the algorithm as a list of words with different weights. And in the table, they are ordered from the most important to the least from left to right. Topics can then be labeled according to our domain expertise and knowledge. And in particular, after the labeling, the prevalence of each topic in each report can be computed through a probabilistic method. So as you can see in the table, the 12 topics were fire extinguishing, workload, departure operations, traffic circuit, weather, go-arounds, sector operations, communication, descent, coordination, alert, and military operations. And as you can see in the pink graph below, they are present so with different frequency in the reports. It is particularly interesting that some intrinsic to the system feature like workload is quite frequent. It is in about 40% of the reports, while some exogenous characteristics like weather or military presence or fire extinguishing is quite less frequent. The second part of exploratory data analysis is clustering. In particular, we defined and described each report via the presence of the topics, which I just mentioned, and other available information in the report. For instance, the main cause of the incident and the main contributor to the incident. The main cause is, for instance, wrong resolution, wrong clearance, unfulfilled VFR procedures, level bust, late detection, and so on. And thanks to this numerical feature, we are able to describe each report in a quantitative way, and then we can cluster them in different groups with unsupervised statistical technique called hierarchical clustering. Here you can see the heat map describing each cluster. For instance, we have incidents in cluster 3, which are essentially due to pilot's contribution, and in particular to airspace infringement and unfulfillment of visual flight rules, which are the darkest square in the heat map. Then the largest cluster, cluster 5, seems mainly composed of wrong clearance and late detection incidents, with clearly the highest frequency of ATCO contribution. And it is also interesting to see that there is a high prevalence of descent topic, while cluster 8 is composed of 3 incidents only. The main topic is fire, and indeed they are the reports referred to fire near Valencia in summer 2018. Then the second step of our work is an algorithm able to automatically extract Tokai taxonomy factors. TOKAI stands for Toolkit for ATM Occurrence Investigation, and its taxonomy is particularly interesting in the sense that its factors are neutralized. So from a resilience perspective, it seemed useful to us. It seemed suited for this work. Here you can see the results of the algorithm on an extract of a report. For instance, in this extract, the sector CAO authorized aircraft 2 without detecting aircraft 1. So the algorithm outlines that there is a taxonomy factor A1, which is about perception. Then the subject was sector CAO, and then the form of the factor was negative because he did not detect the aircraft. And so, for instance, on the last sentence, which is sector ESS provided traffic information to aircraft 1, the algorithm outlines that there is an A4 taxonomy factors, which is about action, which is providing traffic information, and is positive because he did provide traffic information. How does it work? It takes the report as input and performs a syntactic analysis for every sentence. You can see an example here. So sector SAO instructed aircraft 2 to proceed direct to point Loti. The algorithm understands that sector is the subject, that instructed is the root verb, and that to proceed is the adverbial clause, and so on. After lemmatizing and having a syntactic analysis of all the text of reports, the algorithm takes as input the list of words defining taxonomy factors, which are provided by the user. So for instance, for factor A1, which is about perception, we have the words to see, to detect, to identify, to recognize, and so on. And the algorithm checks if there are corresponding lemmas in the decomposed text of the reports. And then the algorithm checks which is the subject, if the form is negative, positive, and so on. Here you can see a graph showing the proportion of negative occurrences of the different factors in the entire collection of the reports. You can see the yellow shape, which is about ground subject, which are controllers, sectors, ATCOs, and so on. And you can see that the most frequent factors are A1, which is perception. So cases in which they did not detect or did not recognize, and so on. And A4, which is about action. And for flight subjects, which is the pink shape, and it's about pilots, aircraft, and so on, the main negative occurrences of factors are A5, which is conformance to rules or procedures, and A4, which is action again. Interestingly, the majority of actions occurred are relative to lack of conveyance of information if you look at the verb involved. The main limitation of this approach is that we cannot directly validate this algorithm, since we did not have a ground truth classification for each report in terms of TOKAI taxonomy factors. So the first validation is clearly looking at the report, but you can do this on a subset of reports, obviously. So an indirect validation of all the collection was performed in a more approximate way. We built a simple machine learning dummy predictive model, which tries to use the output of the algorithm, so the TOKAI taxonomy factors extracted, as predictive features of the contributor to the incidents. So it predicts based on the factors if the ATCO or the pilots or both contributed to the incident. This is just a dummy predictive model and has no meaning in an operational point of view, but since the factors resulted highly predictive, about 85% of accuracy, we can state that there is a high correlation between the factors we extracted and the contribution, which can make us assess that the extracted information is quite reliable, clearly in a rough way. The third part is instead a real machine learning model, which is really useful on an operational point of view. It is a contribution assessment model, and it aims at estimating the contribution based on the ATC events and the contextual information registered in temporal proximity to the loss of separation. So the model takes as input radar data and ATC events data, and returns as output the probability of pilot responsibility and the probability of ATCO responsibility in the loss of separation. This is not intended to be judgmental or to substitute human investigation. Clearly, it is not. It's not the intent. There are two main intents in this operation. The first one is helping safety practitioners in prioritizing the investigations, since there will be more and more loss of separations detected, even in an automatical way, and we need to have to sketch a rough outline of what happened, the dynamic of the incidents, and in particular also the actors involved, which role do they have. The second ways in which this machine learning model can help is in understanding potential precursors of these loss of separation events. Indeed, the model does not just returns the output, so the probability of contribution, but as you can see in this table on the right, it also returns how important each variable was to predict the final output. So we can find here some precursors that tells us which variables are important to describe the dynamics of the incident and their role of ATCO and pilot. The results are quite promising in terms of accuracy. Accuracy ranges from 75% to 95% according to the specificity, the sensitivity we aim at. But an interesting point is that since the output of the model is the probability of the contribution, we can just decide to trust the probability which are more higher, so where the confidence is higher. And so we can see that, for instance, if we just trust confidence greater than 75%, the accuracy is about 96, 97%, which is really high and reliable. So in conclusion, results are promising in general. The main limitation of this final model, is that we need to integrate other sources of structured data, indeed, maybe about weather phenomena, TCAS activation, traffic load, and so on. But the development of a richer model can really lead to further insights in the estimation of contribution and precursors. Also for the natural language processing part, the work is promising. Future work could validate these techniques on other databases of reports, for instance, UK Airports Board reports. And moreover, these techniques could be tailored to identify factors to be included in safety taxonomies, which maybe are present in reports but not in taxonomies, or even hidden sources of resilient performance based on the presence on the reports. Okay, thank you very much for your attention. I'll be happy to answer any of your questions. And thank you.
Thank you very much, Irene, for the presentation. And we got a couple of questions actually from the audience. If I may start with the first one that's been submitted. The technique that you've presented, can it handle incident reports written from different people? I mean, do we have to set up a predefined template for filing those reports?
Okay, actually, the first two techniques, which are about natural language processing, are tailor-made to the Cyanita report. So we have to understand which is the template of the report. But the interesting thing is that we already started to work, for instance, on the UK Airports Board, another type of report. And for each set of reports, if you redefine the template, the algorithm is quite able to adapt. And so these techniques can be adapted to other set of reports, but they cannot adapt automatically. You have to define the template.
Thank you. And in fact, if I may add a comment to that, looking at your table, the table where you had the different topics, the 12 topics, with my sort of safety manager and air traffic controller hats on, looking at one of the topics was traffic circuit, and looking at the words, they were like downwind, right hand wind, and it feels like almost is like an approach stage of flight for those types of events. I was wondering whether there's a piece of work here as well for the controllers to sort of educate to file the reports using specific keywords to facilitate the sort of the application of of this technique, and maybe there is a piece there for them to be involved and engage with this sort of extraction of information, which would obviously make everyone's lives easier.
Yes, I think that the major strength of the topic modeling is that then it returns also the prevalence of each topic in each report. So it is also possible that a controller just asks the model where that words, the keywords like downwind lag or traffic circuit are present, and checks what actually went wrong in that case with a high granularity even. So yeah, I think it may be useful from an operational point of view for controllers.
Thank you. And a couple more questions from the audience. Next one, do you have a method or threshold to decide which level of confidence is high enough to choose, also to trust that input? How would you choose the information that you're going to trust?
Okay, yeah, I think it is referred to the last model. We just tried to understand what happened at a confidence higher than 75, and the average on the test set is 97% of accuracy, which is quite high. So we think it is possible to trust in the future something like that, but that model is really it's really evolving, and we have to develop more on that, in the sense that it is not so. The idea is not to trust it so much. The idea is that a probability of contribution is output. So you can see, for instance, this controller is 90% probable of contributing, and then the idea is that a safety practitioner investigates on it. So since the idea is not to be judgmental or to substitute the investigation, we did not define the threshold of trust, but an idea of how much you can trust it.
Thank you. Maybe linking it to this last point you just made, there's another question that thank you for the comprehensive presentation, and is asking whether there were an estimate of the errors that the method you analyze could be falling, or is there a plan to provide a figure of the performance of controllers based on that information?
Okay. Yeah, I think it is very much connected to the previous questions. Yes, it is. The idea is to include much more information, both in terms of which data, so weather information, traffic information, and so on, and also in terms of quantity. So we just analyzed 89 incidents, which is a very low number. I think that when this machine learning model will be developed on many more observations and larger numbers, maybe including different nations and different airspaces, this would really be more trustable in terms of estimating the error.
Thank you. I think it was the last slide when you mentioned adding incidents from other sources, like having the UK Airprox board, for instance. And as usual, I think one of the limitation times in our industry is the exchange of information, and how difficult or easy is it to obtain information from other sources in terms of incidents that could be going through this same analysis.
Yeah, the reports are actually public, both Cianita or UCAB indeed. But when you talk about operational data, so ATC events, radar tracks, it is much more difficult indeed. The Spanish data are really high granularity data, thanks to the FARO project and to the collaboration with CRIDA and ANIRE. But it's not really so easy, and maybe it's also correct that it's not so easy to have all this data available.
Maybe as a bit of background for you, the UK Airprox board, for incidents to go to that board, they have to be submitted as an Airprox, either by the controller or the pilot. So there are a number of other incidents that would happen in UK airspace that wouldn't go to the Airprox board, but they're still very relevant because are the sort of occurrences that Cianita would deal with. So it'd be quite interesting to be able to sort of feed that system with incidents from other sources, as you said.
Yeah.
Great. No more questions there. In that case, we conclude this presentation. Thank you very much, Irene, for the presentation. Very insightful. Thanks for your time. And we are going to move now to the next presentation, which is increasing the detection performance of genuine separation minima infringements with XGBoost. and it's going to be presented by Christian Verdonk. Christian is a research and development engineer in ATM at Crida, a research company participated by ENAIRE, INECO, and the Polytechnic University of Madrid. And Christian holds an MSc and PhD in aerospace engineering, both from the Polytechnic University of Madrid. Worth noting that Christian was awarded the SESAR Young Scientist Award in 2020. So I shall hand over to Christian for the presentation. The floor is yours. Thank you.
Thank you very much, Luis. Well, I'm going to start my presentation. Could you please confirm that you can see my screen?
Yep, no problem. Thank you. All good.
Thank you. Well, this paper, it's called Increasing the Detection Performance of Automatic Safety Monitoring Tools with XGBoost. The authors are myself, but I would like to also praise the work of my colleagues Chem, Sia, Miguel Garcia, Diego Piva, and Javier Pereceras. We play different roles in these teams. I act as I would say the project manager, while Chen and Diego worked as the developers of the models. They implemented, deployed the model, and conducted all the labeling. We are going to talk about that now. Miguel Garcia put the model into production every single day. This model is already giving us outcomes, while Javier Perez and the NIDE safety monitoring team provided us with operational knowledge in order to conduct this work. So we are going to first talk about the introduction, a little bit posing the problem that we faced, challenges, the methodology to go with the results and our final results and conclusions. So about the introduction of the problem. So all navigation service providers needs to have an automatic safety monitoring tool. On the opposite to the previous presentation from Irene, all the, well, after reference period one, I think from the European Commission, all the ANSPs were entitled to have this kind of monitoring tools in order to detect, identify losses of separation that are not apart from those reported by the air traffic controllers and the pilot. So in this case, well, this is we need to identify, the main function of this tool is to identify all the separation management infringements, sorry, separation minima infringements, sorry for the miswording there. A separation minima infringements is set between two aircraft is set when these two aircraft and the horizontal and vertical distances fall below given thresholds, an horizontal distance and a vertical distance. These thresholds could vary depending on the operating environment. For example, for en route airspace is 5 nautical miles and 1,000 feet. Normally for TMA, terminal airspace, is 3 nautical miles and 1,000 feet. But when we are talking about final approaches, we can go to, depending on the wake vortex, for example, or other considerations, depending basically on the operating environment of the given airport. The NIRES a SMT tool is developed by CRIDA within the framework of Perseo. That is the tool that NIRE is developed by CRIDA, also Perseo, and NIRE uses this tool as a framework for conducting all the business intelligence about the operations of NIRE. So last year, around these dates, indeed, the safety monitoring tool of NIRE reported that Perseo, that our tool was giving a lot of false positive, and we needed to reduce this drastically in order to make this tool more usable. So this is this was our challenge, our task. Just to give an idea that this tool and this paper couldn't be developed without the core process that was running since 2013. Sorry, this core process for detecting the separation minima infringements computes all the horizontal and vertical distances of every aircraft pair in the Spanish airspace, and all of those aircraft with a horizontal distance below 20 nautical miles are stored and we store them in our database. That is called, we call them an interaction. Here for storing them, we are not considering the vertical distance. After that, after storing, computing geometrically all these separations, we process all of them, and depending on the operating environment, we checked if the separation minima is infringed concurrently in the horizontal and the vertical layers. Due to the granularity or the precision of the mode C, that is 100 feet, it was 100 feet until last year in the data that was reported to us. Here we are not considering, for example, the mode S. We saw that there are, back to 2014, there were a lot of fluctuations in the data, in the vertical data. That created problems and false positives that we try to identify and filter with some heuristics, and also trying to see what were these variations in the vertical mode and identifying strong variations. So this idea was in order to overcome non-genuine separation minima infringements. As an example of a non-genuine separation minima infringement would be this case. You could see this figure comes from the Perseo HMI, and we have different elements here. We could see the minimum horizontal separation, but also the minimum vertical separation. We could see in this graph that there was a jump in the vertical separation between these two aircraft that was due to, we don't know the reason, but it was a jump. Couldn't be uh, different reasons, but we need to identify this in a large basis. We identify this, we develop these filtering steps, but the 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 business, the safety practitioner, the safety monitoring team of ENAIRE told us that the performance was not enough, and then what we needed to overcome this. So the first step was try to define what was our actual performance. So in order to do that, we consider the typical, I would say, performance metric for classifications: sensitivity, specificity, false positive rate, precision, and the F1 score. So for the testing data set that we consider, we had a very high sensitivity, but the specificity was very high. That resulted in a false positive rate of almost a 30%. That means that almost between 1 out of 3 and 1 out of 4 cases that were reported by the tool were false positives. At the end, this was giving a really high workload to the safety practitioners of ENAIRE, because they needed to discard a lot of problems, a lot of cases that were not relevant. So in order to overcome this, we last year we set a task force in order to try to solve this. So also we need to consider that the fluctuations were identified at aircraft level. So some of the losses of separation were actual losses of separation were hidden, because the fluctuations were happening when the vertical separation was even below, it was 0 feet, and that even these cases were being hidden. Sorry. So we had a good sensitivity, but the false positive rate degraded our precision. So then the goal of our project was to provide to the safety practitioner a list of genuine separation minima infringements occurring within a given period and airspace, minimizing the number of non-genuine. So we were looking for minimizing the false positive rate. The scope of this specific project was the Spanish air route and route airspace, so above flight level 245. The object is we define this problem saying, okay, we need to discriminate between genuine and non-genuine, so we go to a binary classifier, and the challenges were these two that are described now. First, the model should be embedded in the extract, transform, and loading processes that feed grid as data warehouse every single day. And that was a and that is a challenge because it's a production environment, and we needed to put our model there directly. And also, we need to retrofit our model to the data store from 2013. And the problem is that well, this is a limitation because we couldn't introduce newer data or um, mm, complex transformations because of the large times computation times that we are going to require for this. So in order to do this, we conduct a typical data science lifecycle process. So first was the data understanding. We conducted a taxonomy of cases of anomalies that we could find in our data. And together with the operational experts, we classified if these were genuine or not. Finally, we prepared the data and we selected a sample for training and testing, and also we selected the features, uh, a set of features considering these limitations that we have talked before. About the modeling, we select a algorithm for this classifier, for identifying this for this classifier, and also we conduct a basic hyperparameter finding for this modeling. And finally, we verify the results, yeah, and validate the results. So about the taxonomy of cases, we have presented in the paper different cases that we have observed in the vertical profiles. I'm going to talk here about just these two, but there are more cases in the paper. So we label this with different, starting with with in alphabetic order, but in the case A, you could see tracks that were affected by fluctuation or other kind of anomalies. You could see the sample that we have seen before. For example, in the case C, in this case, we classified this as non-genuine, so it was a 0. We shouldn't show this to the practitioner, to the safety practitioner. In the case C, for example, we don't have a fluctuation, but we have an aircraft that is established at a level that is creating a vertical separation of 900 feet. So this was also considered as non-genuine, so we shouldn't show this. I have more slides showing the case B1 and B2, but these are cases where we have the flights established during a short time in a level that um, it's established at, for example, 32,100 feet or 32,900 feet. If I have another aircraft established at 32,000 or 33,000, it's going to create these losses of separation. So after identifying all the different taxonomies of cases and seeing what we are trying to tackle, what we did was select a training for a sample for training and testing, as this is a really uh, unbalanced problem, because luckily we don't have so many genuine separation minima infringements. But on the other hand, these anomalies in the tracks normally occur when two aircraft have crossed in the airspace, although they have separation minima of 1,000 feet. But in those cases is where we have more losses of more anomalies. So NAIRE provided us with a ground truth, so a genuine list of cases, but these were biased towards cases that should be, for example, reported in the CEANITA reports and should be analyzed because they were classified as alpha or bravo. So those that are really putting introducing a risk into the system. But we needed to complement this ground truth that we were able to identify with other cases that actually were in the data set, but weren't reported to by the controllers or the pilots. So in this case, what we did was selecting randomly um, a set of cases, and we labeled them manually with a team within the team. And then the test sample was all the sample from 2020. And now we are going to talk a little bit about the features that we used. About the features, we consider elements that were specific from the Perseo core process. For example, we were talking about the minimum separation, what was the percentage with regard to the horizontal separation minima, the same for the vertical, what was the altitude, the duration, if the aircraft were in a convergent situation or divergent. Also, the reported anomalies as defined by the heuristics or the flight type. Additionally to this, we consider additional transformations that were easily achievable within our ETL process. So we consider the time at the CPA, and with a window of 30 seconds, we consider different transformations like the mean altitude of the aircraft B, the main altitude of the aircraft A and B, considering also the unit of the altitude, and also the standard vertical separation and the horizontal separation. These features were easily extractable from all the data that we have since 2013 for all the cases. After this, considering these features that we thought that could reflect somehow these jumps, these anomalies that we were seeing, we looked for a model that could be easily deployable in our system, and that was probably the main reason, not only the performance, but the main reason was for selecting XGBoost, that is extreme gradient boosting, is that it is easily deployable in our Java-based ETL pipelines. Okay. Later on, we are going to see a slide that I can go a little bit on these details. For the upper parameter selection, we use the sklearn package, and we use the grid search and cross-validation method for finding a set of hyperparameters that were maximizing our performance. So in our case, our objective function was a binary logistics, because it was just a classification between genuine and non-genuine, and we tried different hyperparameters from the maximum depth or the shrinkage of the on the algorithm. Well, this that you can see in bold, you could see the hyperparameters that were finally selected by the algorithm. So on the results that we had, you could see that the blue points were those that were classified. This is the testing data set. Okay, the blue points were labeled as genuine, and the red points were labeled as non-genuine. This one on the right hand side are cases that our filter identified with anomalies. Okay, you could see that our filter was working reasonably well, but we were missing, well, there were some cases that were actually classified as an anomaly, were hidden, but now the XGBoost, this model was showing, okay, you need to show. Okay, so in this case, if we set a threshold of 0.5 for establishing if this should be should be shown to the safety practitioner or not, our results were this. You could see that the filters baseline performance was the one that was reported before, but for the XGBoost, we reduced the false positive rate by 27 points. So actually now we have a much lower false positive rate that was accepted by the safety practitioners. On this figure is also very relevant to see that all these red points here with a very low score probably are actual anomalies that weren't detected from with our previous filter, and now these were totally hidden by in the new version of this tool. So about the ETL architecture and how we have conducted this process, we started with the team of Perseo and Enaire conducting a labeling and we got the training sample and we conducted the training in a XGBoost model. All of this was conducted in a developing environment. Also, we labeled the test sample, and once we got this performance metric, we evaluated if the performance was acceptable or not. In the case that it wasn't acceptable, we were going to conduct more labeling, introducing more training data. After doing this, we conduct an specification on the data that we should be considering in our ETL that are going to be required for the model in order to conduct the interfacing and wrapping of the model. The good thing about XGBoost is that we could train the model in a Python environment, but then we can dump this model directly to the ETL pipeline that we had. And that was very powerful because um, allow us to accelerate the deployment of this model. Finally, in Perseo, we are showing now with we are showing these cases with all the cases are labeled with the threshold. So the practitioner could say, okay, put the threshold in 0.5, or even the practitioner could say, put the threshold in 0.9 if they don't want to see any false positive. Later on, we also have enabled interaction from the NIRE team in order to keep manually updating the ground truth of this label of these cases in order to keep retraining the model and improving the performance. And now this is working in a daily basis, and every single day we are conducting this, or we are applying this model to all the separation minima infringements that we may have in the Spanish airspace. So for the conclusions of this paper, we have presented this how we deployed this machine learning model, XGBoost in production, retrofitting for the data available since 2013. We presented a series of taxonomy of vertical anomalies in the tracks, and also the features that we have used for our models. The performance of the model was verified with our colleagues of NIRE, and they said that was acceptable. And the false positive rate decreased from 27 points, so it was a really sharp increase in our performance. And then during this year, we have deployed this in the DMA. We have validated that it's also working, and now we are working on extending this to the final approach and the wave vortex separations. The deployment and final to conclude, for us, this was a way of really getting a data set of separation minima infringements that was reliable. So we are talking that more than 30% of we have passed from a 30% of the cases to a 3% just with a simple deployment of this model. We think that with this in a daily basis and so on, for example, we can study all the trends or study situations in precursors in given airspace and so on and so forth. So this finishes my presentation. Here you can find my contact and also Chen contact, that she was in charge of deploying the conducting the training. I'm happy to take any question.
Thank you very much, Christian. Thank you for the presentation. We don't have any questions from the audience. However, I would like to ask you one question. Let's say we put this into practice. We're going to an NSP. We're going to start operating this. I think you explained during the presentation that it's a way of alleviating or reducing the workload of safety investigation department or safety practitioners, that they don't have to look at all these events. And you've shown the improvement in sort of the accuracy of the system. However, from a safety perspective, my question would be about the false negatives. What happens with the false negatives? Because they will still need to be analyzed. Does that mean that we still need a human element of overseeing the system to make sure that we don't miss those false negatives that might have some crucial information from the operation?
Yeah. Well, in our case, I can only talk about our case. Okay, the false negative were mostly not because of because the model and the entire process wasn't able to identify them, but because we had data leakages in the middle. So we had some flights in the database that were not analyzed, and that those were the main sources of false negatives. So not false negatives, indeed, like these are not in our data set for the analysis. This could be because of many different reasons. In the Spanish case, in CRIDA's data sets, for example, the data sources are not very well linked between them, and there are some military flights, for example, that we are not having the flight plans, and therefore we don't have that in our database in the same process. We need to take into account that this is now like talking about 6,000 flights every single day. We have really many millions of flights here, and we can have these data leakages. But from our view, what we have seen here from our data is that we are not having false negatives. Okay, false negatives in the sense of that these cases that we're not showing. But for example, the false negative that could be here. Okay, these blue points below the threshold, we are getting, or we are this data is there in the database. Okay, it is not that we are not showing that directly to the it's not that we are not I would say, let me rephrase this. The false negative is stored in the database, and the practitioner could see it if he lowers the threshold. Okay, the data is always there, but we need to put a threshold at some point, and we saw that 0.5 was working well. So yeah, I mean, we need to pay this. We have this trade-off. Okay, if we want to reduce the false positive, we need to pay the price of some false negatives that are not being shown in the data in the HMI. But in our case, and this is the practice that I would recommend, store always the data and give the practitioner the ability to lower this in case of there are some elements that are not shown. Okay.
Thank you very much, Christian. I'm a bit conscious of the time. We're a few minutes behind for the third presentation. So just to let you know, Christian, there's a question for you in the Q&A window. If I could please ask you to address that question during the next presentation. But if you don't mind, we're going to move on. Thank you again for your presentation. We're going to go to the final presentation of this session, which is going to be wake vortex detection by convolutional neural networks. And it's going to be presented by Boris Resnick. Boris is a systems architect at GLONASS Union, a non-commercial partnership for the development and use of GLONASS-based products and services. And Boris holds an MSc in computer science from Lomonosov Moscow State University. Thank you very much, Boris, and I shall hand over to you.
Yeah,
the floor is yours.
Thank you for introduction. A short note on affiliation. This is an independent research conducted together with Nikolai Baranov from the Rodnitsyn Computer Center, and it's called Wake Vortex Detection by Convolutional Neural Networks. And actually, I will be quick. Please confirm that you see everything normally.
Yep, all good, thank you.
Great. So the problem is kind of well known. Wake vortices can present a considerable hazard for smaller aircraft flying behind heavier aircraft. And today, the only means to cope with this hazard is operational, essentially increasing separation distance, and that affects overall capacity. And there is a good reason to try and reduce it. However, nowadays, what we need to try and reduce that separation without affecting the safety is to try and measure directly the vortices, and that could be done in several ways. One of the means to measure vortices and detect them potentially is LiDAR technology. And first, I'd like to present a measurement setup. Hardware setup used to measure and detect the vortices by the means of LiDAR. So we have here the runway from the top and runway from the side. So LiDAR is positioned sideways to a runway and scans in a vertical plane orthogonal to runway center line, put in the immediate vicinity of a runway. Generally, the distance is about from 100 and 600 meters, and elevation is set so that the scanning captures the whole zone where a vortex generated by an aircraft can potentially exist. So this picture shows like a cross section with a glow slope marker, and the LiDAR scans up, down, and up, down. So that is a setup. So what is the measurement? So LiDAR is a complex thing, but for us, it is important that it outputs a set of scans as a digital data, where each scan corresponds to a single path of LiDAR scanner's motion and each elevation angle. So, and at every scan point, LiDAR senses a projection of a wind speed to a scan line, and it does it on a set of at a set of distances. So each single distance we acquire that speed, so we can present a single scan as a function in polar coordinates, with ranging from actually that's 0 or a half of a degree to like 30 degrees, and with angular resolution of half of a degree, and range is about 3-meter resolution. So we have a grid in polar coordinates represented here as so today there are wake vortex detection algorithms, but they are based on direct analysis of wind speed projection. So as a rule of thumb, a high gradient value span, that speed change the sign. So in some vicinity, direction of speed goes in positive, so from the LiDAR, or to negative direction to the LiDAR. That means that the air is kind of rotating, and that constitutes a presence of a vortex. So this is a kind of heuristic rule, and it is based on current algorithms. There are advantages to that method. It can yield coordinates and also kind of estimate of circulation strength of a wake vortex, but it works under some heavy assumptions about the geometry of the vortex, and also it is highly dependent for distribution of radial wind. And if you scan things near ground plane or low altitudes, and the interference with the ground plane creates secondary structures which violate these assumptions. So we cannot really rely on that algorithm. So and this research made an approach to use neural network to detect wake vortices from the LiDAR scans, and it seems that its approach can be less sensitive to that a priori vortex structure assumptions. So what we do to reuse well-known neural network architectures and not to invent the wheel, we try to represent a wake vortex as an image. So we use a kind of deterministic transform from to acquire an red, green, blue image from in again deterministic way from a wind speed way. And then we have a matrix. Actually, it's just an image which can be represented by this this matrix. So here we have an example of a typical scan, and like you can see by visually that there is a disturbance here, which is a very typical wake vortex generated by a heavy aircraft. So the idea is to detect the same things, not visually, by a trained neural network. The problem here is that there is not much data of potential images of the vortices coming from real measurements, and like a work to label such data could be very time consuming and labor consuming. So we apply another approach based on modeling. There are models which generate that wind speed in quite an adequate way, taking parameters of the scanning, the aircraft type, essentially its weight, wingspan, and things like this. Also ambient conditions like wind. So we choose like well-known types of aircraft. You can see it here, some Boeing, some Airbuses. We choose several scan delays parameters, some typical heights to some ambient wind conditions, and we have a set, essentially a product of all these choices, and gives a total number of samples of around 3,000. And it gives like a pure wake vortex picture. You can see here, like visually, it's very similar to what we have in the measurement, but it's computationally generated. See, okay. So the next issue here is that a generated thing has a very smooth background, which is not the case in the real life. So what we do is we go through like less time consuming labeling process when we label images that are just a background without any vortices. I'm sorry. without any vortices on this picture or on these samples, but they represent some different backgrounds which can be acquired in a real measurement. So, and we perform a blending process based on wind speed behind. But here we have a representation of a blended speeds in a resulting form of an image. So it has numerically modeled vortices together with the background. Okay. So, and these images constitute a training set. So we use like a very standard, well-known convolution neural network architecture here. It's not tailored for this particular task. It's faster RCNN with inception with V2 architecture pre-trained on the COCO data set, and a TensorFlow library is a basis for this network in terms of implementation. We train it for only one single class, that is a vortex, with 200,000 training steps, with more or less standard sampling of 80% for training set and 20% for testing set. So, and validation is done of set of real measurements, which are all labeled manually. This is a sample of detection results based on that validation set, and we can see that this example was chosen as to show that the vortex detected has a very irregular structure. Generally, it is not detected by it may be not detected by a ad hoc algorithm or like direct analysis algorithm, but it is detected by a network. The only note I want to add for this is potential direction of further research. First of all, it is done on a static image, only one scan. However, scans are dynamic and they follow one by one, and that could be employed to enhance the detection results. The second is to perform numerical validation of that direction quality. However, it comes with some issues because the ground truth is hard enough to establish here, but it should be done. And the last two things are more probably advanced, is to try to approach it with a tailored CNN architecture instead of a standard one. And the last one probably is to go directly into polar coordinates, because this is all done in Cartesian coordinates. So that's it. Please, any questions?
Thank you very much, Boris, for the presentation. And yes, we do have indeed a question from the audience, which is how long is the pulse duration used to create the data set?
400 nanoseconds.
400 nanoseconds. Thank you. And maybe if I may, obviously, we have seen how neural networks can be used to interpret that data from the LiDARs. Where do you see this going forward? Is this something that could be used to redefine the wake vortex categories of aircraft by getting a more sort of accurate information about the behavior of the wake vortices, particularly close to the ground during the approach?
Yeah, well, actually, we can ground our assumption on the capability of modern networks to match human in that regard. So as humans can generally do it, at least can tell, like jumbo category against medium category and real waters against some discrepancies generated by the wind on the ground. That is visible. If you can see, then given more data and more validation, we can have a very confident detection by the networks. And even I can say that after some validation, we can also talk about operational deployment of this thing, because real-time detection is very fast and can be efficient enough. There are like reliability questions in this, of course, but level of determinism for operational things is like higher, required much higher than for post-processing, but I'm quite sure that it could be overcome. And
thank you, Boris. There's another question from the audience saying, is there any possibility to use this prediction somehow for fellow fly? If you're familiar with fellow fly,
probably not.
if we could maybe ask Soner to maybe explain a bit what you mean by fellow fly. People might not be familiar with that platform. If it is a platform, I'm certainly not familiar with it. We'll give him a couple minutes. Hopefully we get another question. Yes, have a look at this.
Maybe he's referring to formation flight, Luis.
I'm not sure actually. It says fellow flight, which I'm not familiar. This is a comment that says, oh, formation flight. Okay, yeah, it is formation flight. That's not a term we use in ATC, certainly. So fellow flight maybe is a formation flight Airbus project.
Yeah.
Familiar with that, Boris?
No, but probably I can comment on this anyways. This thing is ground-based, as you see, and I would assume it is not fast enough to support formation flight, because it is a highly dynamic thing. If we move the LiDAR on board, then it is a task which is approachable, but it is much more complex because geometry of the scans are very different. This scanning is done in the orthogonal plane, and that gives us a lot of data on that wake water structure. But if you scan forward, you receive other kinds of data. And again, speed and resolution of the LiDAR, these requirements would be much higher. So I would be careful about this.
And I suppose the way you're measuring wave vortices is sort of on the final approaches of flight duty approach. So you wouldn't be able to apply this technology for, let's say, the en route environment to understand what happens at those levels. Obviously, we wouldn't have the scanners up there.
Yeah. Forward en route, it would require forward-looking LiDAR with very fast scanning, very high resolution, very complex scanning pattern, and even given all these things, I would be very careful without further research to comment on how feasible that would be. At some point in the future, yes, LiDARs evolve, but nowadays it's a tricky question enough.
Thank you very much. Thank you, Boris. I believe there are no more questions. Thank you very much for your presentation. Appreciate it. And that concludes the safety session of this 11th SESAR Innovation Days, which I hope you found as interesting and as insightful as I did. At this point, I would like to thank the presenters, all of you for attending, and the organizers of the event for making this safety session possible. As you're probably familiar with the sessions, we're now going to move to the posted teaser videos. But in the meantime, I hope you enjoyed the rest of the event, and I wish you all the very best for 2022. Thank you very much, everyone.
Hello, everyone. Let me introduce our poster related to FARO project. FARO is one of Year 4 projects funded by SESAR joint undertaking under the topic Safety and Resilience. FARO stands for Safety and Resilience Guidelines for Aviation. Project consortium consists of 7 partners. Project coordinator is CRIDA, and other partners are ENAIRE, Eurocontrol, Universidad Politécnica de Madrid, University of Belgrade, Lund University, and Zenabite. There are 4 main goals of FARO project. One is to define safety and resilience framework, then to propose and develop models for safety performance analysis and resilience analysis. Finally, to do the validation of the developed models and their integration, followed by definition of safety and resilience guidelines as the final goal of FARO project. Currently, FARO project is at validation stage. So if you're interested to see how we plan to do validation, please do visit our poster where we are going to explain that in more details. Thank you.
This is SafeOps, a SESAR-funded exploratory research action. SafeOps envisions a big data-driven predictive tool to forecast go-arounds, and by this, support air traffic controllers with their decision-making in complex situations. In SafeOps, the team investigates the potential benefits of such predictive decision support on safety and resilience of air traffic management operations. But also, we research the potential arising risks introduced by the probabilistic information provided to air traffic controllers, which is inherent to big data applications. Sparked your interest? We are looking forward to engage with you at the SafeOps virtual poster booth.